for giving me an opportunity to share or to speak on basics of the magnetism. I'll share the screen.
Sir, you are a co-host, so you can share your screen.
Okay, okay. A lot of noise. Do you see the screen?
Yes, sir, we are able to see your screen.
Screen. Okay.
This is not your first. We are on the second slide, I think. Second or third. First, can't see your first slide, sir. The introductory slide.
Okay. I request everyone to switch off. I request everyone to switch off your mic. Hello. Hello. Am I audible?
Yes,
There
yes,
is a
sir,
lot of
you are
noise.
audible. And we can, sir, we have muted one participant.
Okay. Thank you very much.
Unmuted, sir. Yes, sir.
Okay. Now, today I'm going to talk about certain aspects of the magnetism, some basics of the magnetism. I understand that the participants are undergraduate students and postgraduate students. Just to get me an idea about who are the participants and to what level I have to explain, I would like to ask the question to the student participants. What do you know about magnetism? Some representative answers are expected. So if the students are there and if you know something about the magnetism, what do you know about magnetism? Would like to answer this question, participants? Is there anybody who wish to answer? Okay. I think there might be some problem with the communication as well, but I'm very sure that everybody from the childhood are fascinated about the magnetism. At some time or other, you came across a magnet, you must have played with the magnets and you must have experienced mysterious force which comes into picture. I'd be happy if I could keep the lecture as an interactive lecture rather than one way I'm speaking and this other way you are listening. So like in between, I may ask some of these small questions, very simple questions. I would be happy if you could participate and if you could reply in response to my questions. Okay. This aspect of magnetism is very old one. And this aspect of magnetism have started for more than 2,500 years back. And for the first time, a rock, namely the magnetite, was observed, which had shown the magnetic properties, which have shown that there is the existence of a mysterious force. Later on, a lot of study has been carried out, even though the researchers worldwide are working on different aspects of the magnetism. Still, the interest in the area of the magnetism has not vanished, and day by day new thing comes, and new physics you have to, or new science you have to find out. Again, whatever is known, even after the time period of 2000 or more than 2000 years, is not, it's very small, it's like a peanut, and there are many things which needs to be still investigated, and therefore the researchers worldwide are working on different aspects of the magnetism. Today's lecture, I have kept it very simple so that lucid, so that everybody can understand. As I was talking about the magnet, or the force experience, the mysterious force experienced because of the magnet. The force basically is because of the pole state, which is there associated with each pole, and it varies as a function of a distance between, or it varies inversely as a function of distance between the pole pieces. The mysterious force which one experiences is typically given by F is equal to K into P1, P2, or P1, P2 that can be considered as a single pole piece, and it is inversely proportional to square of the distance. If you take the proportionality constant K is equal to 1, D if it is expressed in the centimeter, and F in this dyne, then this force experience is expressed as F is equal to K into P into H. So H, this is a very important term, and if you substitute the proportionality constant as a 1 and the pole strength as a unit pole strength, then if at the unit distance of 1 centimeter, if the force experienced is 1 dyne, then that particular pole strength or that particular pole can be said as a pole having unit strength. Okay, so unit pole is a field of 1 over state, is acted upon by a force of 1 dyne. So when you take 2 pole pieces and keep them 1 centimeter away from each other, if the force experience is 1 dyne, then you can call this field as a 1 over state. Now, this is how the, one can understand what exactly the mysterious force, what has been observed. It can be quantified and it can be expressed in certain units. So, like, to give more clear idea about what is the force experience. The force experience by because of the magnetic pole pieces is basically expressed either in terms of gauge or either in terms of Oersted. So, of course, I will be talking about what is the relation between gauge and Oersted, and when gauge should be used, when Oersted should be used. That I will be talking about. But here we'll assume this as a 1 Oersted. So basically, it is something related to the number of lines of forces crossing, or passing through an area of 1 centimeter square. So one line, suppose if I take an area of 1 centimeter square and only one line is passing, then the field can be designated, or field can be called as a 1 Oersted. If 2 lines are passing, then 2 Oersted. Now suppose if I increase the area to, let us say, 4 centimeter square, and if 4 lines are passing, then it should be only 1 Oersted and not 2 Oersted. So this is how you can define 1 Oersted. 1 Oersted, this is also called as 1 Maxwell per centimeter square. So 1 line per centimeter square is 1 Oersted, or that is also called as 1 Maxwell per centimeter square. So this is one of the important term used as far as the magnetism is concerned when you are dealing with the mysteries. Now, as far as this magnetism is concerned, there's one more term which is frequently used and which you need to understand. That is what we call as a magnetic moment. So magnetic moment, again, it is a very fundamental quantity associated with the any magnetic entity, which is usually expressed as pole strength into the magnetic length between the two pole pieces. Everybody is familiar with the fact that the magnetic monopole doesn't exist, and always the north and south, or the two poles or two pole pieces exist or coexist. So it cannot be separated. So if you want, or if you ask me to measure or quantify what is the pole strength of a given pole, or what is the magnetic length between the two pole pieces, it is a bit difficult, or it is not possible to measure it exactly. However, their product, that is what we call as a magnetic moment. So that can be precisely measured. Even though this individual quantity cannot be measured precisely, but you can measure the product of these two quantities. So as far as the magnetism is concerned, you always come across the term what you call as the magnetic moment. Now we'll just first of all try to know the know-how of the terms and terminology. We'll try to understand terms and terminology which are frequently used in the area of the magnetism, and then we will move on to certain examples. Okay. Now, if the other parameter, again, which is very important as far as the magnetism is concerned, that is what is called as magnetization. So in the previous slide, I spoke about magnetic moment. Now here I am talking about magnetization. So again, everybody must have seen the graph of magnetization versus applied magnetic field. And most of the time, this graph is represented for ferromagnetic substance. So ferromagnetic substances is one category of the magnetic materials, and not all the magnetic materials show the similar graph. The magnetic materials, or the graph between the magnetization and applied magnetic field H for different materials different. I'll talk about it in the later part of the lecture. So first of all, we'll try to understand the term what we call as a magnetization or intensity of magnetization. So magnetization or intensity of magnetization, it is defined as magnetic moment per unit volume. So this is the simple definition of magnetization. So magnetic moment, we have seen magnetic moment is product of pole strength into magnetic length. And this particular equation can be rearranged. This is the magnetization, this is the pole strength, and this is the volume. So this can be taken in the denominator. This is volume divided by length, and volume divided by length is what? Area. Or this also can be expressed P by A, or pole strength per unit area. That is a magnetization. So here A is a cross-sectional area of the magnet, and M is a pole strength per unit area, and M is expressed is in the earth per Ohm. Now let us try to understand what is this magnetic moment and how one can define the magnetic moment. Or like for that, let us take into consideration an example. Let us take the bar magnets and arrange in this manner. If you arrange in this manner, like if you put the two bar magnets of equal size and shape and put one over the other, the south and south matching, and north matching. So here, like the pole strength has become two. Like if I assume that P is a pole strength per unit area, then if I increase this area, then it become 2P. Pole strength has become 2P, and the distance, the hypothetical distance between these two pole pieces, I can call this as the same as L. So here the magnetic moment has come as a 2 into P into L. Whereas in other case, if I arrange this way, then here the length has increased. It has become 2L, and the pole strength of a single pole is as it remains same. So in both the cases, the magnetic moment has come the same, 2 into P into L. Okay. So this is how one can find out what is the value of magnetic moment associated with a particular magnet. This example I have given because you must be familiar with the bar magnet. You must have handled it many times. Therefore, the bar magnet example is good. And now, if you want to express this magnetization, so magnetization is usually expressed in terms of erg per Oersted centimeter cube, or this is erg and Oersted. These are the CGS units, or this is also expressed as a EMU per centimeter cube. Now, it is very interesting to tell you that this EMU, this is electromagnetic CGS unit. But if you ask me to just define what is one EMU, it cannot be this. Whenever the EMU is written, it means this quantity, this magnetic quantity is expressed in CGS unit, and the centimeter cube is written over there, means it is expressed for a unit volume. That is what is the convention. Now, you know, this magnetization usually it is expressed per unit volume. Okay. But you know, like if I take into consideration the same substance, but if the way in which it is packed, if it is different, then the volume of that particular substance cannot be measured exactly, accurately. And therefore, it is sometimes a bit difficult to express this quantity in per unit. Therefore, the mass is very small. Mass of this small sample can be measured very accurately as compared to the volume, and therefore the mass is used to express the magnetization, because the mass is also independent of temperature, whereas the volume may change as a function of temperature because of the thermal effect. And therefore, the another term comes into picture, that is what is called as specific magnetization. So magnetization, basically, it is the ratio of magnetic moment to volume, or magnetic moment per unit volume. So this can be expressed in CGS unit, and usually, as I'm talking about volume, so I can express this in per centimeter cube. But taking into consideration in difficulty in measuring the volume, it is many times it is expressed in terms of specific magnetization, and the specific magnetization is written, or it is expressed as magnetic moment per unit mass, M by W. And you know, mass per unit volume is what is the density, and therefore this mass can be expressed in terms of the density and volume, and therefore M by rho into V, that gives you the specific magnetization. Now, the magnetization also that is also expressed for per unit mole, per unit cell, per unit formula, per formula unit, etc. So these are the different terms and terminology which are used to express the magnetization of the given material. Okay. Now, let us try to understand, like, what this magnetization is, and whether what is its relation with the other magnetic quantity. So to understand this, one has to take an example of solenoid. Now here you can see, this is the picture of solenoid. I hope you know the solenoid. Do you know solenoid, students? Students, do you know what is solenoid? Hello? Hello, are you there? Guys, please respond.
Sir, yes, sir, yes, sir, yes, sir, yes, sir.
Okay.
Yes.
Okay. So, anybody want to tell what is solenoid? Is there anybody who wish to tell what do you understand the solenoid?
Shivangi?
Okay. Anyway, so solenoid is basically, it is a some base is taken onto some base. The conducting wire is wound. So you can even consider a pipe, PVC pipe. On PVC pipe, if you wind the conducting wire, that is copper, and if you allow current to pass through, then that is what you call as a solenoid. And there is one what you call as an endless solenoid. Endless solenoid is what? A ring. On to the ring, the wire is wound and current is allowed to pass. So there are mainly two kinds of solenoids, endless solenoid and just solenoid. So if I take into consideration a solenoid, and if I allow to current to pass through the winding, then there is a generation of magnetic field. Now you imagine a small cavity is drilled over here, and here whatever let us at point P, I want to see what is the situation, or how is the magnetization over there. You will see at this particular point there is a generation of magnetic field, or magnetic dipoles are present over there. Those typically have got the poles as a north and south. North is like the right side of this, left side of this particular figure, and south is a right side of the figure. So here, like the magnetic lines of forces are passing from north to south. So the applied magnetic field is from left to right here. And because of this applied magnetic field, depending upon the medium, whatever is present, if the medium or inside the solenoid, that is also magnetic, then that will also get magnetized. Now, because the material inside the core is also getting magnetized, and there would be certain lines of forces because of the applied magnetic field, these two gets added with each other. Now, you know, the applied field H, that is acting from left to right, as far as this particular figure is concerned, that is going to magnetize the material, and north and south poles are produced on the surface of the imaginary cavity. And the material which is used at the inside the solenoid, if it is ferromagnetic, then the intensity of magnetization that would be addition of this M and H, and not only H, because if you not only M, but it would be 4 pi. 4 pi is solid angle all over the in all direction. So it is going to be H plus 4 pi N. So total, so that is what is called as the total number of lines per centimeter cube. That is what is called as magnetic flux density, or that is also called as induced magnetization. And induced magnetization is one of the important terms used in the magnetism. Therefore, from this particular figure, you come to know that this quantity B is higher as compared to the H and 4 pi N. This is because the quantity B, that is the induced flux density or induced magnetization, that is also expressed as B is equal to H plus 4 pi M. So this is very important relation as far as the magnetism is concerned. Now, this particular equation, this H is equal to 4 pi Ni upon 10L, is the intensity of magnetic field generated because of the current passing through the solenoid. Again, you must have studied in your graduation class. Okay. Now, here you can see the quantity B, H, M. This quantity looks like to be same. So that is the lines per centimeter square or Maxwell's per centimeter square. But different names are given. Why different names are given? Different names are given under different circumstances. Here I'll be talking about most frequently used unit, that is gauge and oersted, as far as the magnetization is concerned. So basically, a Maxwell or single line per centimeter square is usually designated as a gauge when it refers to B. B means the previous, this B. B is what? Induced magnetization or magnetic flux density. So magnetic flux density B is expressed as H plus 4 pi M. And when you are using the B as a term, then it is designated as a gauge. And these are the CGS units. And it is designated, or this is the written as the oersted when you refer to H intensity of magnetic field. Okay. Now, when you consider the medium or the magnetic medium. So magnetic medium, if it is air, then for magnetic medium, this magnetization is going to be 0. And if I substitute M is equal to 0 in this particular equation here, then it becomes B is equal to H. And therefore, you can call B is equal to H. So usually it indicates 1 gauge is equal to 1 ounce, or gauge is equal to gauge is unit of magnetization, and this H is a unit, or overstate is a unit of thank you. So 1 gauge is equal to 1 overstate, because for air M magnetization M is equal to 0. So when you are using the CGS unit, it is usually written as EMU per centimeter cube. But when you are using 4 pi m as y-axis of the curve, then the gauge is written. So gauge is written because this indicates you are taking into consideration the contribution from the total flux density. So therefore, that is to indicate that you are taking into consideration. Okay. So the magnetic properties of the material are characterized not only by the magnitude and sign of the magnetization, but also the way in which M varies with respect to H. And here, again, we are going to introduce one more important parameter, that is the ratio of magnetization versus the intensity of magnetic field H. Okay, and that is known as the susceptibility. The susceptibility of magnetic material, that is taken as a base for categorizing the magnetic materials into different types. Okay. Now here, this chi, that is susceptibility, is given as M by H. M is what? Magnetization. What is the unit of magnetization? It is ampere centimeter square by centimeter cube. So effectively it comes out ampere per centimeter. And H also has got unit of ampere per centimeter. So M has got same unit, H has got same unit. And therefore, the chi is dimensionless, or it is the unitless quantity. It is just the number. So M is a magnetic moment per unit volume, and therefore chi also refers to, the susceptibility also is referred to unit volume. Sometimes this is also called as volume susceptibility, and it is given by the symbol. It is the chi V. It is symbol used to designate this as a volume susceptibility. Okay. Now, is it only the susceptibility, or it is only the parameter which is used for expressing the susceptibility? No, there are even other parameters, what you call as a mass susceptibility. As I was talking about the specific magnetization before some time, similar to that of magnetization, specific magnetization is something related to the susceptibility for unit mass, or the atomic susceptibility. So the mass susceptibility is expressed as EMU per overstate per gram, and where rho is the density of the material. And now atomic susceptibility is one more parameter, or molar susceptibility is other parameter. So if it is for a fixed value of atomic weight, then it is more atomic susceptibility. If it is for fixed weight of the fixed molecular weight, then it is the molar susceptibility. And for yes, if it is for unit quantity, then this can be expressed. Check. So this quantity, if it is expressed for unit molar weight, molecular weight, or unit atomic weight, then accordingly it can be expressed in terms of molar susceptibility or atomic susceptibility. Now, susceptibility, as I told you, that is very important parameter. And again, whatever is the level of study, many times the variation of susceptibility is usually taken into consideration to decide the category of the magnetic material. Now, first of all, before going to the susceptibility, we'll like to have a look at the graph between the magnetization with respect to H, that is intensity of magnetic field. Now, if you take into consideration the paramagnetic substance, So paramagnetic substance consists of the individual magnetic moments which are aligned and those are random, in a random fashion. Now, if you take into consideration the net magnetization produced by the paramagnetic substance at room temperature or normal temperature pressure conditions, then the net magnetization produced by the paramagnetic substance is going to be zero. The reason is the magnetic moment of individual species is going to be randomly oriented, and if you take the vector sum of the magnetic moment, then it is going to be zero. But when you apply the external magnetic field, then the magnetic moment of individual species starts aligning in the direction of external magnetic field, which results into increased magnetization. And this is the curve B over here. The curve B indicates that there is a linear variation of magnetization with respect to applied magnetic field. Now, if you take into consideration the similar graph for the diamagnetic substance, the diamagnetic substance has got the property which opposes the external magnetic field. If you apply the external magnetic field, the magnetization would be induced in a direction opposite to that of external magnetic field. This is the characteristic of diamagnetic substance. Now, when you take into consideration the ferromagnetic substance, as far as the paramagnetic substance is concerned, when you increase the external magnetic field and go on increasing, the magnetization keeps on increasing. On the other hand, if you decrease the external magnetic field, then the magnetization decreases and it follows the same path. It tracks the same path. It doesn't deviate from the path which it has followed while increasing the magnetic field. Similarly, for diamagnetic substances, when you increase the magnetic field, there is a linear, almost linear decrease in the magnetization. And when you decrease the magnetization, there is an increase in magnetization. So this opposite nature is because of the typical response of the magnetic substance to the external magnetic field. When we move on to the ferromagnetic substances or ferromagnetic substances, then the major difference what you see is the variation of magnetization with respect to external magnetic field is not linear, whereas in case of paramagnetic substance, it is the linear. Here it follows non-linear nature. It increases, then reaches to certain maximum value. The maximum value it has possessed is called as saturation magnetization. And when you try to decrease the external magnetic field, then it doesn't follow the same path. It doesn't track the path what was followed while increasing the external magnetic field. And that gives the remnants or that this particular nature. So the track followed or the value of the magnetization, what was observed while increasing the magnetic field is different while you observe it for decreasing magnetic field. And this is what is called as the hysteresis curve. Hysteresis is one parameter is lagging behind with respect to other. Therefore, the observation of hysteresis, this particular curve, MH curve observed for the ferromagnetic substances is called as the hysteresis curve. Now, what difference you see between these two curves for ferromagnetic substances? You see the hysteresis curve, whereas for paramagnetic or diamagnetic substances, you do not see the hysteresis curve. There is no lag behind nature observed in case of paramagnetic or diamagnetic substances. The nature observed for antiferromagnetic substances is something similar to that of the ferromagnetic substances, but this statement is a conditional statement. Now here, as far as the susceptibility is concerned, here, like for paramagnetic substances, as I already told you that the for paramagnetic substance or any magnetic substance, the susceptibility is a ratio of m by h, m to h. And this being a linear, whatever is the segment you take into consideration, this susceptibility is going to remain constant. It is same for all the regions of the applied magnetic field. Same statement is true even for the diamagnetic substance. Even though it varies negatively, if you take the ratio of m to h, it is going to be same for all segments or whatever range of the measurement you have used for your experiment. On the other hand, if you look at the ferromagnetic substances, then here it is not linear. In this region, the susceptibility is different. Here it is different. If you increase it further, in this region it is different. If you go to the saturation, it is going to be different. While decreasing the magnetic field, it is going to be different. And therefore, the variation of the susceptibility as a function of external magnetic field at a given temperature is going to be different for different magnetic field. This is the characteristic of ferromagnetic substances. Now, if you take into consideration the variation of susceptibility for the antiferromagnetic substances, then from low temperature, if you start increasing the temperature, the susceptibility increases. And then after particular temperature, the susceptibility decreases. Whereas the variation of 1 over h, 1 over chi as a function of temperature, 1 over susceptibility as a function of temperature, this variation is many times used to find out the magnetic nature of a given substances, and it gives a peak, it gives a deep value in the 1 over chi, and this particular value is associated with the transition temperature. Now, what is the transition temperature? The transition temperature is the one above which the magnetic nature of the material is different, and below that the magnetic nature of the particular substance is different. For example, even if I take into consideration the ferromagnetic substance, and if I go on heating the magnetic substance, then what will happen? This area under this curve will keep on decreasing, and area under the curve is decreasing, and at a particular temperature, the area under the curve would vanish. The area under the curve is vanished means this ferromagnetic material has transformed to the paramagnetic substance, and this is what is called as transition temperature. So the temperature at which such a transition takes place is what is called as the transition temperature, or as per the ferromagnetic substance is also called as, it is Curie temperature. For the antiferromagnetic substances, it is designated as a Néel temperature. So this is what is the characteristic of antiferromagnetic substances. So up to the Néel temperature, the substance is in the antiferromagnetic state as far as the antiferromagnetic category is concerned, and above the transition temperature, the substance is in the paramagnetic stage. So in this case, the paramagnetic or antiferromagnetic character is dominant. In this case, the ferromagnetic character is dominated. So here, in case of B, the paramagnetic character of the magnetic material is dominant, and in case of A, the diamagnetic character is dominant. Now, what decides which nature has to be dominant? So that also can be expressed, or that can be discussed separately. Susceptibility is one of the important magnetic parameter, which is used to categorize the magnetic substances. Similar to susceptibility, there is other term, what you call as permeability. So permeability, in other words, it also expresses as ability to permit, is a permeability. Ability to permit what? Magnetization. So when you take into consideration different substances, if I take into consideration glass, and in other case the iron, one more case is, let us say, copper, and if I start applying the external magnetic field, if I consider glass and if I apply the external magnetic field, what do you think? What will happen? What is going to happen if I apply external magnetic field to glass? What will happen? Anybody has got any idea? Do you have any idea what will happen if I apply external magnetic field to glass? Glass is an example of diamagnetic substance. Now you tell me what will happen if I apply the external magnetic field to glass. Is there anybody who wishes to answer? The glass being diamagnetic, it will be repelled and the magnetization. Yes, magnetization would decrease, right? So that is what is going to happen in case of glass. And in case of ferromantic substances, it is going to, so now in case of iron, copper, nickel, so nickel, copper, cobalt, nickel, cobalt, iron, these are the examples of the ferromantic substances. If I apply the external magnetic field, then the substance is going to get magnetized. But the amount by which it is going to get magnetized is not going to be the same. It is basically decided by the permeability. Higher is the permeability, higher would the magnetization induced into the material. So you know, like before, sometime we have seen the relation. The magnetic flux density or induced magnetization B is equal to H plus 4 pi m. And now, if you divide each term by H, then this equation becomes B by H is equal to 1 plus 4 pi m by H. So m by H is the susceptibility and B by H is the permeability. So permeability is proportional, directly proportional to chi. That is what is higher is the value of chi, higher would be the permeability. Or on the other hand, permeability is higher, susceptibility is also higher. That is what you can say. Or if the susceptibility is higher, permeability is higher. Now here, this mu is not the slope of dB by dH of the BH curve, but rather is the slope of a line from origin. Now here, why I'm saying so? Because the value of B by H, B to H, this is not going to be same for the ferromantic substances. For different segments, it is going to be different. So initially, this value is going to be low, and that is usually designated as mu naught. And that value reaches to certain maximum value, then that is what is called as mu m. So when you are characterizing the magnetic material, usually these two terms are used. Mu naught, that is what is called as initial permeability, and there is another term what you call as maximum permeability. So initial permeability is the slope of the B to H curve, which is recorded at the beginning by drawing the tangent line at the beginning. So this slope gives you the value of initial permeability. Whereas when it is the maximum, then or this curve gives you the value of maximum value of the permeability. So maximum permeability. Now you know, like the solenoid we have, whatever we had considered in that solenoid, the magnetic field at the center of the solenoid having number of terms is equal to n and length of L and current passing through, if I assume that as a I, then the magnetic field produced is expressed as H is equal to NIL by A. And if I define this for the unit turn, then this is called as ampere turn per meter. Okay. So the magnetic moment M is produced by the current I flowing around the loop of the solenoid having the area of A, and therefore it has got unit of ampere meter square. And magnetic moment per unit volume, that is a magnetization, it has got unit of ampere meter square by meter cube, that is ampere per meter. So magnetization also is expressed in terms of ampere per meter. Now these are the different terms and terminology which are used while expressing the magnetization. Now the magnetic permeability and magnetic susceptibility, these are the interrelated terms. So the increase in magnetization when the magnetic material is placed in applied magnetic field, then it is measured in terms of magnetic permeability, how fast or how quickly it is going to, how largely it is going to magnetize, that is expressed in terms of the permeability. So it represents the magnetic field per unit magnetizing field. This is the effect of B to cause H at a given point of H. And now if you are defining such permeability for empty space, then this is what is called as permeability for free space. The permeability of free space is usually taken as a reference, and its value is going to be 4 pi into 10 to the power minus 7 Tesla ampere per meter. Okay. Now, if the empty space in a solenoid, if it is replaced by some magnetic substance having sufficiently high permeability, then the permeability is expressed as the relative permeability, and relative permeability is a ratio of mu to mu naught. Mu is a permeability of that particular material, and mu naught is permeability of air medium, and therefore the induced magnetic flux density B is expressed as mu naught mu r into H. Now, this particular term is analogous to dielectric constant, which is very frequently used in case of dielectric materials. Okay. Now, here, like if you talk the similar thing in terms of susceptibility, this M by H is going to be the susceptibility. So, BH, initial magnetization curve of ferromagnet, gives you value of initial permeability, and its value when it reaches to the maximum, it gives the value of the maximum permeability. Now this is, yes, yes. Up to what time I have to continue? I can continue, madam. Hello.
Yes, sir.
Up to what time I can continue?
You continue, sir. At per your wish.
Because I have collected so many things, and you know, it is going to take long time. It's not going to finish quickly, because as you told me that the audience is a student category. Therefore, I have kept this particular lecture as a simple.
As per student convenience, those things they are understand that much you have to explain them. The things are related to research. We can skip that.
No, I have not included anything related to the research. All the things are related and at basic level. Maybe I'll try to rush very quickly, and if anybody has any question, they can ask me. Okay. Now, you know, whatever we have talked about till now, this is very commonly, those are very commonly used terms and terminology as far as the magnetization is concerned. Now, let us flash some light on why only particular substance, or why the substance is magnetic. What is the origin of the magnetism? It is something related to the structure of the material. The structure of material consists of the atoms, and atom consists of electrons, protons, neutrons. All these are charged particles. Even though the net charge on the neutron is 0, it has got some magnetic moment. The proton is also charged particle. The new electron is also charged particle, and the electron, proton, neutron is going to make the atom. So atom is also charged particle. Before making this statement, I would like to say that whenever there is a flow of charge carrier, then there is a flow of current. And whenever there is a current, there is a magnetic field. So that you know. So the magnetic moment associated with the current loop is typically given by mu m is equal to I into A into mu n. So this gives you an idea about the magnetic moment associated with the current flow. Okay. Now, you know, so like when I consider the loop, so there are two magnetic moments associated with the charged particle, and more specifically, I'm talking about the atomic electron. The electron, which is revolving in an atom with respect to nucleus, it has got two kinds of angular momentum. That is the spin angular momentum and orbital angular momentum. And because of this spin and orbital angular momentum, it has got the spin magnetic moment and orbital magnetic moment. Now, you know, the magnetic moment of an electron due to its motion, that can be calculated. Usually, it is calculated as area of the loop into current. As per the Bohr's theory of the atom, the electron move with the velocity v in a circular orbit of radius r. Then, if you choose this CGS units, then typically this calculation tells you that the the magnetic moment can be expressed as E by C into V by 2 pi R. If you opt CGS unit, and it would be E into V by 2 pi R if you opt the SI units. And if you want to find out the magnetic moment, then it should be area of the loop into current. Area of the loop is pi R square, current is Q by T, and this Q by T can be further solved by using this time is equal to this time is distance by velocity, and this particular equation for the magnetic moment can be rearranged, and it gives you the magnetic moment associated with the current loop is EVR by 2C. The C term comes into picture when you opt the CGS unit, and when you opt the SI unit, it EVR by 2. So, like, you know that angular moment of an electron must be an integral multiple, and that again is based on the Bose theory of atom. Then angular momentum and the magnetic moment, orbital magnetic moment and orbital angular moment are always directed in a opposite direction. So the magnetic moment associated with the orbital motion is, if you do the calculations, then it comes out EH upon 4 pi m. And this is what is the fundamental unit used to express the magnetic quantities. Now here, because of both the spin magnetic moment and orbital magnetic moment, this can be calculated. The spin magnetic moment can be calculated as EH upon 4 pi m into C. And if you substitute all this value, this comes out 0.927 into 10 to the power minus 20 Earth per O state, or this is also designated as EMU. As I already mentioned that when I'm designating, when I'm calling it as EMU, it means it is the CGS unit. And if I opt the MKS unit system, then for MKS unit system, this can be EH upon 4 pi m. If I substitute all these values, this comes out 9.27 into 10 to the power minus 24 joule per Tesla or ampere meter square. So joule per Tesla or ampere meter square, this is the same. This is when I take into consideration the spin and the spin magnetic moment associated with an electron. Similarly, if I take into consideration orbital magnetic moment, then the quantity also comes out to be the same. Again, you can express this in terms of different units. Okay, so depending upon the material, like the material behaves, sometimes it behaves as ferromagnetic, sometimes it behaves paramagnetic, antiferromagnetic, and so on. This is basically decided by what is the content of the material and what is the situation as far as the magnetic moment alignment is concerned. As I had mentioned that the atom consists of electrons, protons, and neutrons, or positively charged nucleus and negatively charged electrons. Electrons are revolving around the nucleus. Now, once again, if you go back to the magnetic moment contribution because of the spin and orbital contribution is usually not taken into consideration. This is because when the charged particle is revolving around the nucleus, the effect due to the half part of the orbital motion gets cancelled because by the other part, and therefore usually its contribution is getting cancelled. But in certain cases, it gives negative contribution. So negative contribution is because the orbital magnetic moment is something related to orbital current. Orbital current in the sense the velocity with which the charged particle is moving. If it is taken into consideration, and if you consider the velocity of the charged particle in presence of external magnetic field, then that velocity is lower. And because velocity is lower, it gives reduction in the magnetization, and that is what is the cause. It gives the diamagnetic character. You know, when you take into consideration any substance, it consists of electrons which are revolving around the nucleus. And when you are subjected to the external magnetic field, it is going to give contribution in the same way. But in addition to that, there are other contributions. As I mentioned in one of the graphs, that in one particular graph, the ferromagnetic contribution is prominent. In other particular graph, the antiferromagnetic contribution is dominant. So which contribution is dominant, that is going to decide the overall nature. And therefore, overall, the magnetic moment of a material is typically decided by the content of the material. There are certain substances, the ionic solids like NaCl. So these, like here, I just wanted to mention, like the spin magnetic moment of a particular electron is getting cancelled by the other. Then there is no net magnetization, and such a substance behaves as a diamagnet. If it is not getting cancelled, then it behaves as a paramagnetic or ferromagnetic. Whether it has to behave as a paramagnetic or ferromagnetic, it depends on the kind of exchange interaction it has got. So again, I will not go into the details of this, but if somebody asks the questions, I can just discuss in the detail. So these are the contributions to the magnetic moment of an atom. Mainly, there are two contributions: the orbital angular momentum and spin angular momentum, and the change in the orbital magnetic moment induced by the external magnetic field. It is the negative, and therefore it gives the diamagnetic contribution to the substance. Whereas these are the details about the calculations about the orbital magnetic moment in presence of external magnetic field. And similarly, these are the details of the electron spin moment. Now, like as I was talking about the why the particular substance behaves as a magnet, ferromagnetic, and others as a paramagnetic. It's basically decided by the electronic configuration of the material. Just a minute. I would like to just tell you about. So there is one slide which I wanted to show you to just give an idea. So what this says. Okay, I hope you can see this slide. Can you see this slide? Okay. Now here you can just have a look at it. So here, for example, if I take into consideration different atoms of vanadium, chromium, manganese, iron, cobalt, nickel. So this has got electronic atomic number of 23, 24, 25, 26, 27, 28. Now, if I take into consideration, let's say iron. Iron, this is the last electron contribution, last orbital contribution of the electronic configuration of iron. So here you can see this particular state has got two electrons which are aligned in direction, or whose spin magnetic moment or spin angular momentum is aligned in direction opposite to each other. But there are many others which are not paired. These are going to contribute to the magnetic property of the material. Similarly, in case of cobalt, also you can see, even though the number of unpaired electrons is less as compared to iron, but there are. Similarly for nickel. And if you take the case of copper, there are no unpaired electrons. And therefore, copper doesn't behave, or copper doesn't show ferromagnetic property, but iron, cobalt, nickel, Mn, these materials show the ferromagnetic properties, right? So whether the substance should show ferromagnetic or diamagnetic properties is basically dependent upon whether there are unpaired electrons are present or not. If unpaired electrons are present, then there is a possibility that the certain substances may show. Sir, मी class मध्ये आहे, तुम्हाला phone करतो. There are certain substances which will have unpaired electron, but the exchange interactions are weak, then it gives the paramagnetism. If the exchange interactions are sufficiently strong, then it gives the ferromagnetism. If there are no unpaired electrons, then it gives the diamagnetism. And this is basically decided by the Hund's rule. Again, I will not go into the details of the Hund's rule, taking into consideration the time constraint. I will not go into the details of the rule. Now here, this data of magnetization can be used to find out the specific magnetization based on the magnetization experimentally what has been observed. And if you just find out to look at the values of the specific magnetization observed for iron, cobalt, and nickel, then you can see iron has got highest value of the magnetization. Again, there is a theory, what we call as a band theory. So again, I will not go into the details. Only thing is that here I just wanted to tell you that, like, when you look at the energy levels, like usually we know the valence, like when you talk about an electron which are revolving around the nucleus, those electrons are revolving around the nucleus in a specific orbit, and two orbits are well separated. The energies between these two are not allowed energy, and there is no possibility having an electron having the energy between the two allowed energy. That is what we studied, and this is very basically true when you talk about the case of hydrogen atom. But when you talk about the multi-electron system, this picture is not very true. So why it is not true? This is because of the charge particle associated with the atoms are not the single atom, but those are the atoms present in the sea of the material, or in the sea of many other atoms. Millions of atoms are present in a particular substance. And when I'm saying there are millions of atoms, this atom consists of the charge particle, namely electrons and nucleus. These electrons of atom A may interact with the atom B, atom C, depending upon what is the distance between the two neighborhood. So that gives you deviation of the energy level diagram or energy level spread that results in the formation of band. Therefore, this is the picture which is used, and that has got very close correlation with the magnetic property. So these are the different quantities which are used, and the units also are very important. And again, I will not name each and every term, but this is what is the data. The conversion of these units with from one unit to other unit is very important. And again, there are textbooks and this data is available in the literature. As I told you that the magnetic substances are basically diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and canted antiferromagnetic. This is another category of the magnetic material. As far as diamagnetic substances are concerned, diamagnetic, paramagnetic, ferromagnetic we have discussed. As far as the antiferromagnetic substances are concerned, the magnetic moments are aligned in a direction opposite to each other. These are some of the characteristics of diamagnetic substances. It has got very small susceptibility with negative of the order of 10 to the power -5. This is a specific character of diamagnetic substances. Paramagnetic substances have got positive susceptibility, but their magnitude is not very high. It is small, and it gives the linear behavior. Whereas ferromagnetic substances are the one which has got large positive susceptibility, and there is a characteristic temperature, what we call as a Curie temperature. Below that, it shows particular characteristic, and above that, it shows some other characteristic. So this is an example of the ferromagnetic unit cell. So in a unit cell, there are different atoms. So the red one, what you see, is individual atom, and individual atom has got net magnetic moment. Now the net magnetic moment of all the species is aligned in the same direction because of the stronger exchange interaction, exchange energy, then the substance is a ferromagnetic substance. So in case of antiferromagnetic substance, if you look at the adjacent sites of the magnetic site, then these are aligned in a direction opposite to each other, and the net magnetic moment of this species is going to be equal and opposite. Equal and opposite means net is going to be 0, and that is what is the typical characteristic of antiferromagnetism. Whereas in case of ferromagnetism, the alignment of magnetic moment is similar to that of the ferromagnetic substances, but the magnetic moments are aligned in direction opposite to each other, but unequal in magnitude. Therefore, its net behavior is similar to that of the ferromagnetic substances. So these are the different characteristics or properties of the ferromagnetic substances. Now, here there is one very important term which is used for the characterization of magnetic substances. That is what is called as a exchange interaction. Now, you know, like when you talk about the ferromagnetic substances, the magnetic moment of atom A directly interacts with the magnetic moment of atom B, and that gives very stronger magnetic interaction, and that forces the neighborhood substances to align its magnetic moment in the same direction. But there is another category of the metal what you call as antiferromagnetism. So in antiferromagnetism, the magnetic moment of adjacent magnetic species is directed in a direction opposite to each other. The example is MNF system and MNO2 or MNO system. So in MNF system, the magnetic moment or magnetic entities are separated by non-magnetic substance. The fluorine is non-magnetic. In case of Mn oxide, Mn is magnetic, oxygen is non-magnetic. Oxygen ion is non-magnetic. Now, if you look at the alignment of magnetic moment of the adjacent species, here this is aligned in the same direction, but if you look at the adjacent species, it is aligned in the opposite direction. Now, if you just look at this particular picture, if I just take out a small segment out of it and present it over here. Now, here what you can see, when I consider two Mn atoms which are far away from each other, then it will have its magnetic moment independently, or the Mn atom would be behaving independently. But when I try to bring, or when I try to decrease the distance between two Mn atom through oxygen. So here, this is Mn, and this is oxygen. Now, when I try to bring these two closer to each other, then what will happen? The magnetic moment of the Mn is going to interact with the magnetic moment of oxygen. Even though the net magnetic moment of oxygen molecule is going to be zero, because it has got the cancellation of spin magnetic moment of two electrons outside with the oxygen. But when the Mn atom comes closer to each, then there will be interaction of magnetic moment of Mn with magnetic moment of oxygen, and that will displace it from the equilibrium position, and it will establish the interaction between the non-magnetic oxygen and magnetic Mn. So this interaction will be of an antiferromagnetic in nature, and this will align in direction opposite to each other. A similar thing is going to occur over here. This is what is called as super exchange interaction. The super exchange interaction, or it is also called as indirect interaction. So the magnetic entities are going to interact with each other through some medium, through some non-magnetic medium. This is what is called as indirect exchange, or it is also called as super exchange. The super exchange interactions are very prominent in case of antiferromagnetic substances. Similarly, these kinds of interactions are very prominent in case of category of the material what we call as a ferromagnetic material. Again, I will not go into the details of the structures of the ferromagnetic substances. And so the ferromagnetic substances are basically categorized as inverse ferromagnetic, normal, and mixed one. So the nickel ferrite is an example of the ferromagnetic substance, and nickel ferrite or cobalt ferrite, these are the examples of the ferromagnetic substances. Now, if you look at the variation of saturation magnetization in case of the spinel structure, so again, this is when we talk about the details of the, so I will not go into the details of this. Gamma iron oxide is one of the very applied magnetic substance. This also has got the spinel structure, and its magnetic properties can be calculated, magnetic moment can be calculated, which can be verified experimentally. Within the whatever time was allotted to me, I was told that I can talk about 45 minutes or so, but already I have taken about 20 minutes more. than what was whatever time was given to me. So in summary, what we have seen in today's lecture is what is the origin of the magnetism, what are the units which are used, what are the interconversion, what is used for the for expressing the magnetic quantities, what are the types of magnetic material and what are their properties. So what are the properties of magnetic system, what are the different kinds of exchange interaction, what is the ferromagnetic substances, what are the ferrites, etc. That is what we try to discuss in today's lecture. Now, I would like to answer the questions if you have any. So I can see in chat box. It's not; these are not questions. I think this is something related to attendance or something like that. If you have any questions, I'd be happy to answer.
If audience have any question, ask directly or type in chat box.
Hello, sir.
Yes.
Sir, what is the temperature effect on porosity and retentivity and saturation magnetization?
So that depends on the category of the material. If you take into
Sir,
consideration
if
the
material is ferromagnetic material.
then it would decrease as a, with increasing temperature. So there is a transition of
So coercivity decreases and
coercivity and
retentivity.
retentivity both. Coercivity and retentivity both are going to decrease as a function of temperature. If you increase the temperature. Basically,
And
magnetization is going to
saturation
decrease.
magnetization.
That is also going to decrease.
Okay, sir. And sir, one more question is there. What is the difference between permeability and pulse permeability?
Permeability and
Pulse permeability.
yeah, that might be the permeability recorded by giving some pulse of magnetic field. That is the pulse. And permeability already I explained.
Sir, if we have to calculate pulse permeability, then what we have to do?
You have to give some pulse and look at the magnetization. Basically, this is we will use for the paramagnetic substances.
Okay, thank you, sir.
Are there any questions? Any more questions?
Anyone else? Please ask. We move towards vote of thanks. On behalf of CIMET project team, I, Saili Shankar, here to spell out words of thanks to Dr. Mathe sir for such an intellectually stimulating gathering, and also thankful to all faculties and students for joining in. Thank you, sir.
Okay. Should I leave the meeting?
Yes, sir. Now the session is over.